a small town in Colombia became ground zero for a global mystery. A strange metallic sphere, now known as the Buga sphere, fell from the sky, leaving behind a trail of unanswered questions. Is this object a sophisticated?
At first, it looks harmless. A smooth metal sphere sits in plain sight, doing nothing at all. Then, the doubts creep in. The tools give answers that do not match. Experts pause, argue, laugh, then go quiet. How does metal end up shaped like this? Why does it behave oddly under testing? Curiosity spreads, tension builds, and a simple object turns into a serious mystery that refuses easy answers. Nothing about it feels normal, even to people who handle materials daily. But before cameras rolled and experts arrived, one unsettling question lingered. What lay hidden inside, and why defy every test? The discovery. A small dark sphere appeared in a field near the town center of Buga, Colombia, in early March this year. Jose Arias took the first pictures and posted them online, and they started trending quickly. The ball had a smooth surface and a surprising weight. When someone lifted it, the weight did not match what a mere hollow metal would weigh. Technicians moved the object to a nearby workshop for a closer look.
The object was handed over to radiology specialist Jose Luis Velázquez, who brought an X-ray machine to a UFO fight. As for the X-ray analysis, where's the raw data?
A radiology technician named Jose Luis Velázquez offered to image the interior using the clinic's X-ray equipment. The resulting images showed inner layers and small, bright points inside. Those details turned curiosity into a subject that technicians, presenters, and scientists wanted to study more closely. Presenter Jaime Maussan visited and set up public displays to show the materials and the scans. Organizer David Velez assisted with transport and coordination. Teams measured the sphere, weighed it, and set rulers beside it for scale in their footage. People tested simple tools and noticed standard blades and saws had trouble cutting through. In some moments, the work slowed as testers adjusted their approach. Those scenes made many viewers ask what the object was made of and who could explain it. The first handling raised two practical issues. One, many formal laboratory tests require paperwork and controlled conditions. Two, the group wanted to keep the object intact for later analysis. Those needs shaped the early choices. Non-destructive checks came first: X-ray imaging, magnet tests, and surface probes. By design, these checks preserve the object while giving scientists clues. Some reported that the surface resisted ordinary tools. Others said water behaved oddly near the ball, and that a hand held close felt cooler than expected. These reports added interest. Engineers and materials scientists watching early materials asked for measured thermal studies and specific instrument logs rather than casual notes. Several institutions expressed willingness to help. Public messages named the National Autonomous University of Mexico as able to assist if given access. Private laboratories in Colombia offered imaging and analysis. Funders stepped in to cover transport and test fees. The handlers balanced the urge to share results with the need to protect evidence for careful scientific work. Legal questions about ownership and sample handling also shaped the early path. Documentation mattered. Viewers and experts wanted full records, such as who handled the sphere, exactly when it moved, and the exact settings used for each machine. Early posts sometimes left out full notes. That gap made it hard for outside teams to repeat procedures and confirm observations. Scientific practices rely on clear records so others can check steps. Public attention grew fast. Journalists covered the story and sent the images to the public. The exposure helped bring offers for testing, but it also created pressure to release quick conclusions. Some specialists asked for calm steps like securing transfer to accredited laboratories, independent imaging under controlled settings, and careful calibration of equipment. Several named people stayed central to the early record, including Jose Arias, who took the initial photos, and radiology technician Jose Luis Velasquez. Images showed concentric rings and small, dense points that drew technical attention. Those inner features led engineers to note that manufactured objects sometimes use internal weights or sensor modules placed at specific points. Specialists asked for raw X-ray files so they could review angles, exposure, and machine calibration. Multiple labs requested secure transfer to repeat scans. The next phase required clear custody, formal lab chains, and agreed testing plans before any destructive samples could be transferred. Donors and volunteers helped pay for travel and advanced imaging. Technicians documented the route with time-stamped photos to back up the chain of custody notes. Several teams prepared formal requests to receive the object under controlled terms so they could run spectrometry and microscopy when allowed. The early period moved the sphere from a single field into a wider investigation. Volunteers, technicians, and named presenters coordinated tests while scientists called for rigorous methods. How the object was handled and documented in those first days shaped what tests became possible later. Careful steps ahead would be needed to build a full technical picture. But before scanners spoke, one fragile decision loomed. Would early handling unlock truths or quietly contaminate everything to come later? The X-rays. When the sphere reached the clinic, radiology technician Jose Luis Velasquez set it on the table and ran X-ray scans that changed people's perspectives. In the images, the shell did not look empty. Instead, the pictures showed at least 3 layers and a cluster of small, dense points inside. Those bright points stood out because they blocked more X-rays than the surrounding material. Different images gave different counts for those points. Some photos suggested 9 of them, while others hinted at 18. That difference came down to how the machine was set and the angle used for each shot. X-ray equipment works by sending radiation through a material and recording what comes out the other side. Dense parts stop more radiation and show up lighter on the image. Lighter parts let more radiation through and look darker. One still picture flattens depth. To see how parts sit in 3 dimensions, technicians rotate the object and take multiple images from different angles. Changing the energy of the beam also changes what the picture reveals. A higher energy beam will go deeper and show inner structure, while a lower beam highlights surface detail. These explain why 2 labs can post pictures that do not look the same. The scans also showed thin lines that linked some inner points. On a 2D image, those lines look like threads or narrow rods. In real objects, such lines can be wiring, small supports, or shadows where parts overlap. Radiologists who reviewed the public images warned against quick conclusions. Angle, exposure, and machine type change how features appear. That is why raw image files and machine settings matter. Raw files include calibration marks and exposure numbers that let other teams recheck how the photos were produced. Some viewers named a well-known university as the source of the clearest images. That claim raised expectations, but no official statement from that university confirmed working in the sphere. Without clear confirmation, many experts called for open access to raw scans. When raw scans are shared, independent teams can reprocess the data and test alternative interpretations. That transparency is how professionals rule out artifacts and confirm real structure. What do the rings suggest? Concentric layers mean different materials stacked in order. Engineers build layered spheres to control weight, manage heat, or shape signals that pass through the shell. Inner dense points can be counterweights, structural anchors, or housings for sensors. On a clear, high-resolution scan, a solid insert will show a sharp edge. If the pattern is a single material with density gradients, the image will show smooth transitions instead. Repeat imaging under known conditions is the only way to tell which case fits this sphere. Technicians tried both low and high energy modes when equipment allowed. Combining settings gives a fuller view. Hospitals have standard X-ray machines that show internal shapes. Industrial computed tomography systems, which rotate the object and build a 3D map, provide much clearer internal detail. Many specialists recommended industrial computed tomography at accredited facilities to build full 3D maps and to measure density values at each inner point for clear analysis and timing. Experts also asked for calibration tests. Scanning a small object of known density alongside the sphere demonstrates whether the machine reads density correctly. Those checks help rule out machine error or image artifact. Without them, an odd picture could be the result of overlap or shadow rather than a true physical part. In public, the images were shown as stills and short sequences. Viewers noted the rings and the bright points. Scientists kept a consistent message, saying the scans were interesting but not definitive. To move beyond questions, the sphere needs repeatable imaging, shared raw data, and industrial-level scans that build 3D models. That route turns curious pictures into a measured structure. Could a manufactured device produce the same pattern? Yes, a crafted sphere with shells, inner modules, and thin routing traces will look similar on X-ray. That option gives a clear, testable explanation that fits the images. To confirm any idea, experts must run repeat scans under agreed standards and then compare results. Until that is done, the X-rays remain a strong clue, but not a final answer. But if images mislead, what happens when scientists move beyond shadows and test the real substance itself for hard answers? Material tests. After the X-ray images, they focused on material tests to learn what the sphere is made of. The first steps used non-destructive checks, so the object stayed whole. These tests give useful indications, but they do not show the exact chemical makeup. Workers measured mass and size to estimate density. Density helps tell if an object is a light metal, like aluminum or steel, or a heavy metal, like tungsten. Several people who lifted the sphere noted a weight that did not match its size. A heavy result can mean a dense inner core or a solid metal shell. To be reliable, mass and diameter need exact measurement and careful notes about how the volume was taken. Magnet tests came next. Technicians used strong magnets and simple compasses to check magnetic behavior. Iron-rich alloys pull strongly when a magnet approaches.
Iron is magnetic. Nickel is another metal that's able to be magnetized or attracted by a magnet. Also steel. Well, steel contains iron, and so that's the reason why. Or if it contains any magnetic material, if it's an alloy.
Non-magnetic metals, ceramics, and many composites do not react. Some tests showed little magnetism, while others showed a weak pull. Differences in results can come from a thin outer coating, a mix of internal materials, or magnets with different strengths. Clear magnetometry uses calibrated instruments that measure magnetic moment rather than casual hand magnets. Inspectors looked at the surface for seams or finishing marks. At first glance, the outer skin looks very smooth. Close inspection with magnifying tools and angled light revealed areas that behaved like a thin coating rather than bare metal. Modern casting and polishing can hide joints. A smooth shell can mean careful manufacturing rather than a single cast. Specialists used small brushes and cleaning steps to see if any outer layer flaked or dissolved. Where a coating exists, it can affect surface spectrometer readings and hide what lies beneath. Thermal behavior became a key topic. Proper tests use thermal cameras and digital probes to record temperature over time. Recorded trials measured surface temperature while applying a controlled heat source, and while cooling the object with a known chill. Some trials showed the surface warmed slowly under steady heat. Other trials recorded a small cooling effect in measured conditions. These mixed results need repeat trials with controlled timing, identical sources, and logged sensor outputs to be useful. Portable spectrometers offered an early look at surface elements. Handheld X-ray fluorescence units detect elements on the surface without cutting. Initial runs showed peaks that did not match a simple single alloy. Handheld devices are useful for quick checks, but they read only the outer layer and require careful calibration. For exact element percentages and trace elements, laboratories use mass spectrometry or inductively coupled plasma analysis.
ICP-OES, which means inductively coupled plasma optical emission spectrometer. Sample is introduced into a nebulizer. The nebulizer turns the sample into tiny droplets.
Those laboratory methods can reveal minor elements and precise percentages that show whether a metal matches common industrial mixes. Deeper work requires small samples. Metallography studies metal under a microscope after a tiny cut and reveals grain patterns and heat treatment history. X-ray diffraction shows the crystal structure. Mass spectrometry measures isotope ratios that can point to where a metal came from. Those tests are destructive and require written permission plus a strict chain of custody. Engineers offered practical manufacturing explanations that fit the visible signs. A layered shell can be made by casting, by layered deposition, or by nesting pre-made shells. Inner dense nodes can be balancing weights, housings for electronics, or anchor points for structure. Thin internal traces might be supports or small routing paths. Research teams building sensor spheres and experimental devices have used similar layouts. Such human-made assemblies would appear on X-ray as rings plus internal bright points. If teams want firm answers, they must agree on a test plan. Useful steps include exact density checks with calibrated equipment, magnetometry with known field strengths, thermal cycling with data logging, laboratory mass spectrometry, X-ray diffraction scans, and optical microscopy of any cut sections. Independent laboratories should run parallel tests and share raw data so others can reprocess results. Clear records must go with every test. Notes should show who handled the object, the time and location of each step, machine settings, calibration materials, and raw output files. The material tests so far offer interesting indications, but no final answer. If handlers permit full laboratory analysis, specialists can identify alloys, coatings, and isotope fingerprints that point to industrial sources or to unusual compositions. Further independent tests will decide whether it is truly unusual or common. But when evidence met publicity, did careful science stay in control, or did spectacle begin steering the investigation itself forward? Expert views. When the sphere moved from the field into the hands of presenters and technicians, responses split into clear groups with different aims. One set of people pushed the story into public view. Jaime Maussan held public showings where technicians displayed the scans. Radiology technician José Luis Velázquez presented the X-ray images. David Velez helped move the object between testing locations and kept basic transport notes. Their work brought attention and helped gather offers from outside laboratories. Another set of experts urged caution and careful steps. Radiologists and materials scientists asked for raw imaging files, full machine settings, and complete notes on how each test was run. They pointed out that X-ray images can show lines and bright points because of the angle or machine settings. These experts want repeatable scans from accredited imaging centers and industrial computed tomography that builds three-dimensional maps. With that data, technicians can measure density for inner spots and confirm whether nodes are solid inserts or imaging artifacts. Metallurgists listed the tests they would run if given access. A tiny sample under an optical microscope shows grain patterns and heat treatment marks that indicate human processing. X-ray diffraction reveals crystal structures that point to specific alloys. Mass spectrometry measures trace elements and isotope ratios that can show whether a metal came from common industrial supply chains. Those techniques are standard, but they require a small cut of material. Because cutting destroys part of the object, handlers and institutions must agree on terms before any sample is taken. Private laboratories in Bogota and other cities said they could run calibrated spectrometry and controlled thermal studies. Academic groups prepared formal proposals. The National Autonomous University of Mexico noted specialists who could assist if a secure transfer took place. Independent scientists offered technical advice on magnetometry, thermal cycling, and methodical imaging. Their emphasis was on instruments that produce logged digital output rather than casual impressions. Skeptics pointed to gaps in the public record. Early posts often lacked clear timestamps, signed transfer paperwork, and machine calibration logs. Reproducing a result requires knowing exposure numbers, angles, and calibration references. Without raw data, outside teams cannot reprocess images to check for artifacts. Skeptics also warned against quick public statements. Announcing conclusions before full laboratory analysis can mislead observers and make later corrections harder. Supporters of an unusual origin focused on the combination of features shown in scans. They mentioned concentric rings, inner bright nodes, and reported odd thermal responses. Those elements together seemed different from many common items people come across in open areas. Supporters asked major laboratories to run formal studies and to publish full raw outputs so independent teams can review the work. Several practical rules came up repeatedly. First, record the chain of custody with signed documents, time-stamped photos, and witness notes. Second, share raw imaging files and machine logs so outside teams can reprocess data. Third, run parallel tests in at least 2 independent laboratories to reduce bias and detect lab error. Experts said these steps provide measured, verifiable results that other teams can confirm. Which institutions were named publicly? Reports listed private testing centers in Bogota and research teams in Mexico and Colombia. Assertions that the Massachusetts Institute of Technology supplied the clearest scans remain unconfirmed by any official statement from that university. Many scientists urged caution when institutional names appear without formal verification. Most experts agreed on a clear test plan. Secure the object under controlled custody. Share raw imaging files. Run industrial computed tomography to build three-dimensional models. Perform calibrated spectrometry and thermal cycling with logged sensors. If permitted, take very small samples for metallography, X-ray diffraction, and mass spectrometry. Publish full raw outputs so others can reanalyze the data. How did public attention affect the process? Media exposure brought funding and fast offers for tests. That support sped up transport and imaging. At the same time, it created pressure to give fast answers. Many specialists welcomed public interest, but asked for patience until accredited labs release full data and documented results. For now, the scientific view remains divided between urgent public study and careful, methodical verification. The next reports from accredited laboratories will decide which explanations match the desired, measured results. Watch for full lab reports that include raw files, calibration logs, microscope images, element tables, and isotope reports, so private investigators can reevaluate results publicly. The Buga sphere story is still open, and many questions are unanswered. Investigators and volunteers have shared images and early tests. We need clear, repeatable studies from private labs before final answers. Please like, comment, and subscribe if you want updates. Thank you for watching and for caring about careful science. Follow the channels that publish raw data regularly.